Hey everyone, welcome to CCISD Mission Control. In anticipation of the upcoming Artemis 2 launch, this video is going to go over some of the math involved, specifically the basics of orbital trajectories. My name is Brigham, and I'm a senior from Clear Springs High School. Physics and math are some of my favorite subjects, so I'm excited to be able to share this with you. When people think about space missions, they usually think about rockets, astronauts, or how cool pictures of the moon are. But behind all of that is math. Math helps mathematicians and engineers predict exactly where the spacecraft will be in space. And they don't just figure this out during the mission, they have to know where Orion will be long before it even launches. The path the spacecraft follows through space is called a trajectory. For Artemis 2, Orion uses something called a free return trajectory. This means that the spacecraft is set on a path where gravity naturally helps bring it back to Earth. You can think of this like throwing a boomerang. If you throw it just the right way, it comes back to you even without needing extra effort. Artemis 2 trajectory is designed the same way, so even if the engines stop, gravity helps guide Orion home. Space isn't flat, it's three-dimensional. This means mathematicians can't use a simple map like we do on Earth. Instead, they have to use 3D graphs with three directions, x, y, and z. These directions represent left and right, forward and backwards, and up and down. Orion's position in space is written using these three numbers, one for each direction. Each number tells mathematicians how far Orion is from the center of the graph. It's kind of like giving directions in a video game. Instead of saying go north, you say exactly how far they need to move in each direction. This lets mathematicians know exactly where Orion is in space at any moment. To understand how Orion moves, mathematicians use something called vectors. And a vector just doesn't tell you how fast something is moving. It also tells you which direction it's going in. Orion's velocity is a vector because it describes both speed and direction. Acceleration is also a vector. It tells mathematicians how much force is acting upon Orion and which direction its force is pushing in. So even when Orion's engines are turned off, gravity is still acting on it. Gravity changes Orion's velocity, which is why a spacecraft doesn't move in a straight line. This is how Orion curves around the moon, by letting the moon's gravity gently steer it, kind of like swinging around a pole or swinging around an object with a rope. To model Orion's position, mathematicians start with something called the two-body problem. And the two-body problems look at how two objects move because of each other's gravity, usually a spacecraft and a planet or moon. Both objects pull on each other at the same time, and how strong their pull is depends on their mass and distance between them. These two-body problems were invented by Isaac Newton. For example, Earth pulls strongly on Orion because the Earth is massive. The closer Orion is to Earth, the stronger that pull becomes. During Artemis 2, the math gets more complicated. Orion is influenced by both Earth and the Moon at the same time. This is called a three-body system. Predicting motion in a three-body system is much harder, which is why precise math is so important. A reference frame is basically a point of view used to describe motion. Another way to think about it is asking, where am I standing when I watch this happen? There's no single correct reference frame. Motion can look different depending on where you are. For example, in an Earth-centered reference frame, Earth is treated as if it's standing still, and it's placed at the center of the graph. The Moon and the spacecraft move around it. In an Orion-centered reference frame, the spacecraft is treated as still, kind of like putting a camera at the front of Orion. From that point of view, Earth, the Moon, and the stars appear to move around it. The reason why we use multiple reference frames is because different problems are easier to solve with different reference frames, so mathematicians switch between them depending on what they need to calculate in the moment. First off, a matrix is a table of numbers, and each number has a specific job. Matrices are used because it allows mathematicians to easily change information between different reference frames. They take motion described from one point of view and rewrite it to another point of view. Since Orion's position needs three numbers, left, right, forward, back, and up, down, its speed also needs three numbers. Matrices help organize all that information in a way computers can understand. The reason why we do that is computers are really good at solving matrix math. On board Orion, for example, about 100 math problems can be solved every single second. Even crazier than that, computers on mission control on Earth can solve millions of matrix problems per second. All this math would be possible to do by hand during the mission, so mathematicians create software that lets computers handle the calculations. On board Orion, navigation software uses information from star trackers, gyroscopes, GPS when near Earth, and signals from deep space networks. All these measurements are fed into math algorithms that constantly update Orion's position and velocity vectors. Without this math and software, Artemis 2 would not be able to safely fly around the moon or return home. Thanks for watching. I hope you enjoyed learning about the basics of orbital trajectories. If you're interested in learning more about Artemis 2, please make sure to check out our other videos.